Okay, so we spent a fair amount of time finding real zeros of a polynomial. And what we're getting into here in section 4.5 is getting into possible imaginary zeros. And by an imaginary zero, let me show you what I mean. Uh, this, by the way, is the first of 2 days we're going to spend on this. F of x is equal to x squared plus 4. All right, well, if we graph this, as, let's see, here we are, x squared plus 4. And there we are. We have our parabola. And as you can see, it has y-intercept that is above the x-axis. It's curving upwards, so it never actually touches the x-axis. So based on our definition that we've been using so far of thinking of a zero as an x-intercept, we'd be really tempted to say this one does not have any zeros. But we have to think back to our original definition of a zero. And basically what that is that is an x value that will make the function equal to 0. Well, let's try it out. X squared plus 4. Subtract 4 from both sides, we get negative 4 is equal to x squared. Now, this of course has no real answer, but if we delve into the world of complex numbers, we can find that x is going to be equal to plus or minus 2i. And so we can have imaginary zeros. And the reason that this doesn't show up on our xy plane is because the xy plane deals strictly with real numbers, not imaginary numbers. So what this opens up, or segues into rather, is a couple of theorems which I have joined together into one. Your book writes this out as the fundamental theorem of algebra. And then it has another theorem that is shortly afterwards that really is just a little bit of an extension on it. So I'm going to join the two of them together. The other one is the n zeros theorem. Basically, if we join these two together, I'm going to paraphrase it a bit. All right, that every polynomial, I'm going to call it p of x, polynomial starts with p, of degree n is greater than 0, so the degree is 1, 2, 3, 4, and so on and so forth, has n zeros. And these are not necessarily distinct, and I'll explain what I mean by that in a moment. And can be written as n linear factors. Okay? Now, notice how we did not get into the word real there. Our zeros can be real or they can be imaginary. This is where we're opening up the possibility of having imaginary zeros, which we haven't done before. Here's an example. F of x is equal to x squared minus 6x minus 16. And we could factor that out and write it as x minus 8 times x plus 2. All right, so we have a 0 at x is equal to 8, and another 0 at x is equal to negative 2. Both of those are real zeros, and we can write it out as this linear factor, x plus 2, times this linear factor, x minus 8. So because it is second degree, then we can get two linear factors. Now let me explain what I meant by not necessarily distinct in the theorem above. For example, we could have f of x is equal to x to the 4th. If we wrote that out as 4 linear factors, it would be x times x times x times x. So we have 4 zeros, but they're all at the same place. We have a 0 at x is equal to 0. And it's 4 times over. So that's what I mean by it not necessarily distinct, meaning they could repeat. So if we were to apply this to our earlier problem, right up here, then if we were to factor out x squared plus 4, we would have x minus one number, x minus another number. Now, the 1, 0 would be at positive 2i, so x minus 2i. The other one would be at negative 2i, so it would be x minus negative 2i, which is x plus 2i. So we can still write it out as a set of linear factors, and there's 2 of them, but we have to delve into imaginary numbers to make it work. All right. By the way, before I go ahead, what you'll notice here is that right there, our signs on the imaginary numbers, they switch. We have a positive option and a negative option. We're going to get back to that in a couple of minutes. Let's try another one. F of x is equal to x squared minus 4x plus 5. Doing a quadratic here because quadratics we can solve for 0 relatively easily with a number of different ways. So 0 is equal to x squared minus 4x plus 5. What I'm going to do is I'm going to use a quadratic formula because this is not factorable in terms of real numbers. So x is equal to negative b, so that's 4, plus or minus the square root of b squared, that's 16, minus 4 times 1 times 5, all over 2a, which is 2 times 1, or 2. 4 times 1 times 5 is 20. 16 minus 20 is going to be negative 4. So what we wind up with is 4 plus or minus the square root of negative 4 all over 2. The square root of negative 4 is plus or minus 2a. So we have 4 plus or minus, or not 2a, 2i, plus or minus 2i over 2. So when we simplify a little bit further, we get 2 plus or minus I. So if we wanted to write this as a fully factored form, we actually have not just the imaginary part like we did in our first example, we actually have a full complex number. So our function, f of x, if we put it into factored form, it's going to be x minus, need some other parentheses, 2 plus I, times x minus your other 0 at 2 minus I. So we're still following the same pattern of a second order being x minus 1, 0, x minus another 0. It's just that now, instead of having a nice clean real number there, we have a 0, which is an imaginary number, which we have, or a complex number, which we have to write as a binomial. And so it gets a little visually confusing. So sometimes we would, depending on the application, we would decide to find these zeros and then write it out as x squared minus 4x plus 5 and leave it in that manner just so we can claim that we are keeping it real. Here's something I'd like to point out about these two zeros. Notice how 2 plus I and 2 minus I, they're complex conjugates of one another. Complex conjugates are those numbers that we multiply by one another in order to get a real number. And we used it when we were dividing imaginary numbers quite a bit. So here's another theorem that I'd like to toss out to you. It's called the complex conjugate theorem. Basically, to paraphrase it, it goes like this. If a polynomial p of x has real coefficients and a plus bi is a 0, so is a minus bi. Same thing goes the other way. If you are given a minus bi is a 0, that means a plus bi has to be a 0 as well. Notice how we've seen this already. We wound up with a pair of complex conjugates for the problem we just did, 2 plus I and 2 minus I as zeros. If we go all the way up to the beginning, our first example, we have positive 2i and negative 2i. They are complex conjugates of one another. You switch the sign on the imaginary part of the number. So what this actually does is it essentially gives us a buy one, get one free deal. Because if you find one, then you automatically have found the other. So this can come in handy when we're finding these because it cuts our work considerably. So here's an example of a problem we might come across. Let's say we have a third order polynomial and we're given that the zeros, that two of the zeros are at x equals 2 and x equals 5 plus I. All right, well, if it's third order, that means that there's 3 zeros by the fundamental theorem of algebra. So what we've got is our function definitely has the factors. Now it could have a constant out here, but don't sweat that. It's definitely going to have x minus, say, 2, x minus 5 plus I, and then some other number, x minus, and I've been doing a, b, and c, so I'll just do x minus c. But by the complex conjugate theorem, we know that if we have 5 plus I, that means our next zero has to be 5 minus I. So that gives us this last zero without really having to calculate anything out, x minus 5 minus I. So again, it's just automatically tells us one if we have the other. Another one, before we call it a day. Let's say we have a fourth order polynomial, or a fourth degree polynomial, if you prefer that term. And you have zeros at x is equal to 5i, and you have a 0 at 1 minus 2i. That means that automatically you know that you have another 0 at negative 5i and a 0 at 1 plus 2i. That gives us 1, 2, 3, 4 zeros, which is exactly how many we have. Okay, your practice problems tonight are going to be on page 388. Page 388. What I'd like you to try is numbers 1 and 9 and 10. So number 1, number 9, and number 10. Good luck, and I'll see you in class.